So we can see directly from the prompt here, from the prompt of serial lemma, it used numerous examples to let the lemma model to know what kind of formalization, theorem statement, and what kind of proof the model should output. And after the numerous examples of in-time context learning, after we provide numerous amount of examples, and we expect the model to learn from these examples and give the correct output. It's actually a vast amount of examples. So here we expect the model to give the correct output, correct proof out of this problem. So this is how in-context learning work. Wait a minute. So let's get back. So finally, in a very famous benchmark of Lean, this kind of methods get about 36% of accuracy, which is very high at that stage. It is actually very good, a very good score. So then I will introduce the second techniques. The second technique is called retrieval augmented generation. I didn't type it complete because it's too long. This retrieval augmented generation which mainly means it's firstly used in medical and law aspects, because these aspects we want we also have very few data, but we need the model to give response in very high accuracy, very high quality. We don't want to expect the model to give the wrong answer with respect to medical and law. So what is the workaround to do this? First, they retrieve some kind of information from a large vector data set, which contains maybe many law cases, many medical items. And after this retrieval, we get the more similarity between our problem and the items in the data set. And we use these related items to generate a more accurate response, which may be more knowledgeable, makes the model more knowledgeable and more related. So this is also a very good workaround method. So we can see from the graph in the left-hand side, the right-hand side, if we do not have the vector data set, we ask a problem, the model will respond, no, I don't know about this information. But if I retrieve some information from the data set, from the user data set, and the model will know, it gets the model will know it gets the correct response. Yeah. So this is how retrieval augmented generation work. So how can we apply this method into Lean? This is very fundamental work of automatic prover in these aspects, using LLM to prove Lean theorems, which is called reprover, which is just a shorthand for retrieval augmented prover. Yeah. So how does it work? We can see from the graph here. So every time you want to generate a tactic, it will search in its own theorem database to search for the most related theorems and lemmas, just like you will do in your proof. You want to search in Mathlib for a related theorem to use. So in this framework, the model automatically do this. After it retrieves the theorems it needs, and it immediately insert into the prompt of the tactic generation, or we call it the reference model, and the model will output a more valid tactic to solve the problem. So this is earlier work, so its performance is a little bit bad, but actually it's a very fundamental work in that era, maybe 2021, I believe 2021. And this method we call premise selection, which means we select the necessary lemmas to use. And this is how this paper work. And another work is more progressive. It's more aggressive. It not only use the vector data set. It also interact with the database, which means when this prover do the proof, once it finished the proof, we can see from once it finished the proof, will use an extractor to extract some kind of lemmas to extract some fractions of proof into new lemmas. And they call this lemmas a skill set, which means some knowledge the model gets when it do the proof, and it will optimize this fraction of proof and insert this lemmas back into its data set, which means it will has a dynamically increasing database and when it do the retrieval. So when it prove more theorems, its database, its skill set gets stronger. And not only it can retrieve from the mathlib, ordinary mathlib database, it can also retrieve from its own skill set, which means he can just call some lemmas it proved previously and insert these lemmas into the new proof. So this works more dynamically and will be more flexible and actually result a very good performance on mini F2F. For those unknown, mini F2F, this dataset is a dataset contains theorems lemmas in the high school level and competition level, which means the span of the knowledge is very limited. So when it proves more and more lemmas, prove more and more theorems, the models actually get very high quality information about this benchmark. So it gets a very high score. So why it is called a Lego prover? Because it can split and reconstruct the proof. So it is called Lego prover. But one limitation of this prover is that one known limitation of this prover is that it may be retrieved too many fractioned lemmas from the database, but it does not know which lemma is important or which lemma is mathematically beautiful to use. And so if there's two lemmas for the model to use, model will not know how to combine this lemma to a full proof. So this prover has own limitations, but it's also set a very good example to overcome the knowledge of a large language model. And another very famous technique in the large language model is called chain of thought. Maybe some of you have heard of chain of thought. This is also a very recent breakthrough, not very recent, but 1 year ago, a breakthrough in the formal and informal reasoning in large language model. So what it works, it's in the zero shot version of this sort of chain of thought. We can see from the chart here, we just insert different prompts into the prompt of model before our problem to query the large language model. We can see that if we let the model to think step by step, or think about this following the logic, it will get a very high score. The model will know it first do this, then do this. After that, we do that, and it will output a sequence of response. Then we find that it will get a very good score. But if we input some kind of misleading information, it will actually get a very bad score out of the same prompt. This shows that to structure the output of model or to structure the chain of its output is very important. It can make the performance doubled or even tripled or even improved improved a lot. So this is a work from the 2021, yeah, I think. So now actually this chain of thought has become a standard to aligning the latest large language model, which means whatever large language model you are prompting with nowadays, it will automatically output in a step-by-step way. Yeah, because everyone finds that this is very useful. If you let the model directly output the answer incomparable to the step-by-step then output the answer, it will have a significantly increase in the performance. So this is a typical GPT response. So how can we how can we learn from these techniques in Lean? So actually, to summarize about these techniques, which is actually makes the response more logic-like, which is analogous to a term proof and tactic proof in Lean, right? Term proof is like we give the type immediately, just as I said in the previous lecture. But the tactic proof is like break down the proof into small fractions and do it step by step to finish the proof. This is very analogous. So we can see from here, this is step-by-step proof. So actually, beyond the chain of thought, which comes the most recent breakthrough of large language model aspects, which is called the test time scaling or the tracer or the just R1-like model. What R1-like model does? What it does is just not only it output a chain. When it do the training or do the inferencing, it actually search through a very complex tree to find the most optimal chain to finish the answer. Which with each step, it will find the most optimal, most valid choice of the possible step. And after combining the most possible step, it will get the best result. There's a two kind of guidance about how this kind of R1 model and O1 model do to achieve this kind of tree search. The first one is that like O1 do. O1 do is just for each step, we give it a heuristic. We give it which step is good and which provision of each step, we finally get the best result. But the drawback of this method is that it's computationally expensive, because in each step we need another model to monitor whether this step is good. So what DeepSeek R1 does is that it just do the check in the final step, but in addition to the check of the final step, it do the formal check. It do the this formal check means that it had to be output the language in the correct format. You can only output in the markdown format or in the code format. You cannot output in some random language. Yeah. After the format punishment, just format monitor and the response, the final outcome monitor, it actually saves much computational resource and gets nearly the same performance as OpenAI O1. So that is how DeepSeek R1 like problem that actually impressed everyone. Yeah, all of this is out from just the chain of thought technique. And how can we replicate this method, or how can we learn this in Lean 4? It actually is a similar way, because we can imagine each state or as a node, as a step, and each tactic as the edge connecting different steps. And finally, we find that to find the proof in Lean is actually to traverse a very complex tree, like this I show in the right-hand side. Once you find the good path leading from the maybe this is your statement and the end is a no-goes. Once you find the path like this, you claim that you actually find the correct proof. Yeah, it's basically the same thing as just the chain of thought. So this proof method is called step prover. So now, based on this, I will introduce several recent work about how the state-of-art model do this formalization, do this auto-formalization automatic proof. The first one I want to introduce is the DeepSeek prover. And what DeepSeek prover do is like it iteratively do the proof completion, and once the completion encounters some kind of error, it will backtrace. It will backtrace to a stage where no error occurred, and it will do the regeneration from that state, and until it iteratively finish the goal. So it's actually a different way of tree search, but it turns out this tree search method works very well, and it's use a special kind of tree called Monte Carlo tree search, which means you first do the simulation, you random select the leaves and nodes, and then use your experience to optimize your generator, your proof generator. And this means at the same time you do the tree search, you can iteratively update your generator until it gets a very good state. So it's very performant. It have a good performance. It will reach a very high mean after score, which is at 63%, which is very impressive in 2023, which is last year, maybe in May 2023, last year. Yeah. And now is the most recent SOTA, which is called BFS prover. This is done by ByteDance. You know ByteDance, which is 字节跳动 in Chinese. And what it does is that it uses very simple search mechanism, which is called best first search. It finds the most possible tactic and iteratively finds the next tactic, which is much simpler than Monte Carlo search. But what it does, it do the extra iteration in a very large data set, which means it do the proof on a natural language or the unknown, a statement with no proof. And once you get the proof, it use this new data to iteratively train the old model. And they want to get the better model. And they done it with very, very vast amount of computational resource. And they spend lots of time on this. And they do it at a very extreme parameter because they have very sufficient computational resource. So they get a new SOTA, which is about 70%. It means just 1 year ago, this SOTA is about 26%, which is reprover. And over this past year, because of development LLM of all these techniques, it has come to this 73%. So it's very impressive. It's a very emerging area in the application of LLM. So yeah, that's my point. And another different way to do the step prover. This is also this is a formal SOTA, also very good performance, but it represents a different path to do the tree search, to do the blue search. And what it does is that instead of just best first search, it uses a search called beam search, which is at a certain beam width, search at a certain beam width. But what it do is that it search with a heuristic, which means each time you encounter a proof state, use a tactic to encounter a proof state, it use another model to evaluate whether this state is good or bad. Oh, so it will get how this state is close to the no-go state. So it will use this metric to evaluate whether it is good or not. If it's good, it will get the top priority. It will get higher priority to search, to expand to the next node. So after this heuristic, it will hopefully will get to the no-go state more quickly. Yeah. So I believe this model get about 68 or 70% of accuracy, also very high, and also very effective in terms of this searching mechanism. So I think another graph is that it has many different proof in the iteration. It shows the distribution of proof length, which we can see that there's the longer proof contribute to the less portion of all the proof. Yeah. So it's expectedly after later work, after later progress of LLM model, we are expecting this peak become higher. We are expecting a normal distribution of proof length, which means it can prove some normal difficulty of a problem. Yeah. So I think this is what I'm going to talk about today. There's a different kind of model, different recent progress to automatically formalize. So yeah, previously I will have a demonstration for the function calling because now the server is down, so I have no time. No, this part will be eliminated. Yeah. So I believe that's all for today.